Hello, my name is Chris Benke, an offering manager in the Aerospace and Defense Business Unit at NI. Phased arrays are becoming an important RF architecture in aerospace and defense applications, such as radar and satellite communications. The components and modules used to build these architectures have unique RF characterization requirements that need to be performed to ensure that the end system will perform correctly. As such, NI has released the Electronically Scanned Array Characterization Reference Architecture, or ESA reference architecture for short, which includes all the necessary IP to perform these measurements. In this video, we will show you how to perform pulse profile and pulse-to-pulse stability measurements using the NI vector signal transceiver, or VST. To characterize PAs, or power amplifiers, and transmit-receive modules for radars, it is important to be able to perform pulse measurements, such as pulse profile and pulse-to-pulse stability. Pulse profile, for example, is looking at a single pulse and ensuring that the various attributes are correct, such as state levels, transition durations, overshoot and undershoot, droop, or ripple and ringing. A secondary measurement used to qualify the performance of a component in a radar is pulse-to-pulse stability. This can either be the stability of pulses over an entire chain of pulses, or the stability of samples within a single pulse. In this measurement, you're looking at the stability of both magnitude and phase over time and temperature to ensure that the component or module itself will behave over the operational mission of the end system. The challenges of pulse profile and pulse stability measurements include the synchronization of RF pulse stimulus with the DUT device under test you're controlling to accurately characterize the component stability. The dynamic range and phase noise of instrumentation can negatively affect measurement accuracy. And the limited RF instrumentation bandwidth can reduce your test coverage and ability to meet the needs of more advanced radar applications. Using the pulsed RF measurement library included within the ESA reference architecture, we will show you how to overcome these test challenges and measure both of these parameters accurately. Here, we see the interactive example for pulse measurements included in the pulsed RF measurement library within the reference architecture. In this setup, we will be providing a pulse stimuli to an X-band transmit-receive module typically found in the front end of a radar phased array. We will perform not only pulse profile measurements, but the pulse-pulse stability measurement itself simultaneously using the vector signal transceiver, or VST. As per all of the interactive examples within the library, you are provided the ability to both configure the hardware as well as the stimulus and measurement, as well as in real time view the measured results for interactive analysis. In this particular case, we're using the vector signal transceiver in a shared LO configuration. This allows us to optimize out the phase noise impact of the instrumentation itself, and therefore tackle one of the key challenges of these measurements. This is configured using the panel on the left here, which allows us to select the VST as well as configure the synchronization and LO sharing. In this case, we're tuned to 10 gigahertz, which is at the top end of X-band. You can also configure the stimulus based on things like pulse repetition interval, pulse duration, and the sample rate of the device itself. We support CW as well as other stimuli types within the pulse library. However, in this case, we're using CW for simple stimuli. Trigger settings can also be configured, allowing you to either control the synchronization with the devices under test or take in a triggered result from the device itself, again, tackling one of the key challenges for this measurement. And then finally, you can choose the specific configuration types for the particular measurements, such as your pulse profile and pulse-to-pulse stability. This includes setting where the samples will be within the pulse to provide your statistical result. Once you're satisfied with the configurations of the hardware and the software, you can go ahead and run the measurements, as you see happening right now. Within the displayed measurements, you see multiple displays that can be configured based on your needs. In this case, we're looking at the pulse-to-pulse stability plot, which includes information on the stability of phase, magnitude, and the overall results. You can also look at things such as the amplitude profile, which shows you the pulse profile from the first measurement, as well as the statistical results such as droop, rise time, width, etc. Finally, we have supplementary views to show you additional parameters such as the FFT of the pulsed stimuli itself and the instantaneous values of the measured samples within the pulse for pulse-to-pulse stability. Once you're satisfied with the measurements, or in fact, as you're measuring the experiment, you can record the data for post-processing at a later time. This completes showing the demonstration of pulse measurements and pulse-pulse profile using the interactive example within the pulsed RF measurement library in our reference architecture. As you've seen, we've tackled the challenge of pulse profile and pulse stability measurements, in particular, the synchronization of RF stimulus with the DUT, the instrumentation phase noise degradation, and the limited RF instrumentation bandwidth, simply by using the benefits of the vector signal transceiver. Combining these advantages with our software-defined measurements allows you to tackle the overall test plan and requirements for your PA or transmit-receive module in a radar application. For more information on pulse profile measurements and pulse-to-pulse stability, as well as the ESA reference architecture, please visit ni.com. Thank you very much.